Hello everyone, and welcome to our channel. Have you ever wondered how the universe might end? We know that the universe began with a big explosion, the Big Bang, but could it one day also come to an end? Many theories have been proposed by scientists to explain this, and one of them is the Big Crunch, where the universe collapses into a single point. But this is just one part of the bigger picture regarding how the universe might end. Let's dive into these fascinating theories. Today, we will explore a particularly intriguing but challenging theory about the end of the universe, the Big Crunch. Similar to how the universe began with a massive explosion, known as the Big Bang, it is possible that it could end with a great collapse, also known as the Big Crunch. So, what is the Big Crunch? Simply put, it is a scenario where the universe stops expanding and begins to contract, compressing all of space, time, and matter into a single point. Imagine the universe as a giant balloon being inflated. If the gravitational pull becomes strong enough, it will pull all matter towards the center, causing the balloon to deflate and shrink. As the entire space contracts, everything from stars and planets to galaxies would be pulled together, culminating in a state of extreme density and heat. This theory is not just baseless speculation. In the 1970s, scientists like Stephen Hawking discussed this possibility as they observed the universe. At that time, data on the universe's expansion was still unclear, and there were many theories suggesting that if the mass in the universe were large enough, gravitational forces could overpower the expansion process, leading to a collapse. Remember that gravity is a fundamental force in the universe and can affect all matter and energy. The question then arises, what could cause the universe to begin collapsing? According to the theory, if the density of matter and energy in the universe reaches a critical value, gravity would overpower dark energy, the force causing the universe to expand and pull everything back together. Once this occurs, the universe would no longer expand, but instead would be compressed step by step. However, the Big Crunch theory is not without its challenges. In the 1990s, data from the Hubble Space Telescope indicated that the universe was expanding at an increasing rate, rather than slowing down as the Big Crunch predicted. This led to intense debate among physicists. Nonetheless, the Big Crunch remains one of the key theories for understanding the potential end of the universe. An interesting aspect of this theory is that some scientists believe the Big Crunch may not be the final end, but rather the beginning of a new cycle. The universe might undergo a series of contractions and explosions, creating new Big Bangs after each Big Crunch. This is known as the cyclical universe theory and has been proposed as an explanation for why the universe might be reborn multiple times. While this theory is still debated, it offers an intriguing perspective on the distant future of the universe and how it might end with a massive collapse. It is a thought-provoking scenario that raises questions about the role of gravity, dark energy, and the very nature of space-time. Whether or not the Big Crunch becomes a reality remains an open question, but it undeniably opens new and fascinating directions for research in modern science. Big Freeze is built on the assumption that the universe will continue to expand forever. As it expands, the distance between galaxies grows larger, and over time, stars, planets, and all other matter will become isolated. In this scenario, dark energy plays a crucial role, driving the ever-increasing rate of expansion. But what does this mean for the far-off future? As the universe continues to expand, stars will run out of fuel and gradually extinguish. Galaxies will become cold and dark as no new stars are formed. This gradual decline does not happen quickly, but is a slow, drawn-out process lasting billions of years. According to the theory, all nuclear reactions in stars will cease, and the final remnants of stars will be cold relics, such as black dwarfs, emitting neither light nor heat. To better understand Big Freeze, we need to consider the concept of entropy, a measure of disorder within a closed system. According to the second law of thermodynamics, entropy always tends to increase, meaning the universe is moving towards a state of imbalance and unusable energy. Like a clock winding down, everything will eventually slow and stop. When no more usable energy is available, the temperature of the universe will drop close to absolute zero, minus 273 degrees Celsius, leading to a state of silence and coldness. A simple illustration is to imagine the universe as a hot cup of water. As the water cools, its thermal energy spreads throughout the surroundings, eventually reaching the same temperature as its environment. In the case of the universe, when thermal energy and light can no longer be transferred, it will reach a cold, balanced state with no possibility of regeneration or transformation. A unique aspect of Big Freeze is total isolation. Star systems, planets, and even particles will be so far apart that no connections remain. This means that from a life perspective, all essential conditions like temperature, energy, or chemical bonds will no longer be sustainable. If a civilization exists in this far-off future, they will witness the universe sinking into eternal darkness and complete inability to sustain life. Physicists believe that Big Freeze is a plausible scenario if dark energy continues to dominate the universe. Notably, data from recent astronomical observations, such as from the Hubble telescope and research programs on the universe's expansion, have shown that the expansion rate is not slowing but accelerating, lending further support to the Big Freeze hypothesis. However, the theory is not without its controversies. Some scientists argue that there is still much we do not know about dark energy and how it works. Can dark energy change over time? Could a new factor emerge too slow or even halt the expansion? These questions continue to be explored and debated within the scientific community. While Big Freeze may seem cold and bleak, it is not just a tragic scenario, but a reminder of the universe's fragility and our limited understanding of all the factors that shape its fate. Can we find answers before everything sinks into eternal silence? That is what scientists are striving to understand every day. Big Rip is one of the most unsettling theories about the end of the universe, based on the concept of dark energy, the mysterious force driving the accelerating expansion of the universe. In this scenario, expansion does not merely continue but accelerates to such an extent that it overcomes every force of gravity, weak and strong nuclear forces, and even the bonds holding atoms together. This results in a universe where everything from galaxies and solar systems to planets and the smallest atoms is ripped apart by the unstoppable expansion. The mechanism of the Big Rip begins with the powerful influence of dark energy. As dark energy continues to dominate, it causes galaxies to drift farther apart at an ever-increasing speed. According to some scientists, such as Robert Caldwell and his colleagues, the expansion will become so powerful that it not only increases the distance between galaxies, but also tears apart the bonds between stars within a galaxy. Over time, even solar systems will be torn apart, and each planet will lose its stable orbit. Notably, the Big Rip does not only affect large structures in the universe, but can also reach down to smaller structures like molecules and atoms. When the expansion becomes extreme, the forces binding atoms which make up matter will be overcome, leading to the complete disintegration of atoms. In other words, all known matter will no longer retain its structure, and the universe will be reduced to subatomic particles scattered across vast empty space. An interesting aspect of the Big Rip is the uncertainty of when it might occur. Based on current observations of the universe's expansion rate, if the Big Rip is to happen, it could occur billions of years from now. But it remains unclear exactly when or even if it will certainly occur. This uncertainty depends on the true nature of dark energy, which remains a major mystery to physicists. A story related to the Big Rip centers on the discovery of the universe's accelerating expansion in the late 20th century. At that time, astronomers such as Saul Perlmutter, Brian Schmidt, and Adam Rees measured that the universe was not only expanding, but doing so at an increasing rate. This discovery, made through observing supernova, led to the 2011 Nobel Prize in Physics and reinforced the idea of dark energy's powerful influence. However, the Big Rip is not the only scenario, and not all scientists agree that it will necessarily happen. There are many theories suggesting that the nature of dark energy might change over time, or that other balancing forces could emerge in the future, slowing or even stopping this process. But if the Big Rip does occur, it would mark a rapid and terrifying end, vastly different from the slow and gradual decline of scenarios like the Big Freeze. The Big Rip paints a picture of a universe not just broken apart, but stripped of all form and meaning, leaving behind a void where even fundamental particles no longer exist as we understand them. This relentless expansion is a stark reminder of the mysteries of dark energy and demonstrates that our vast universe, despite its enormity, can be profoundly affected by forces we have yet to fully comprehend. This theory raises questions not only about the fate of the universe, but also about our limited understanding of the fundamental forces that govern it. If the Big Rip is the future, it is not merely destructive, but a reminder of the complexity and ever-changing nature of the universe we inhabit. Alongside major theories like the Big Crunch, Big Freeze, and Big Rip, there are numerous other hypotheses about the universe's end, each presenting a unique and thought-provoking scenario. One such theory is the Big Bounce, a concept suggesting that the universe may not end permanently, but instead contract and then explode again, creating a perpetual cycle of birth and destruction. According to the Big Bounce, after the universe contracts to a critical point, as in the Big Crunch scenario, a new explosion similar to the Big Bang will occur, beginning a new cycle. This opens up the possibility that the universe is a continuous process with no true beginning or end, but instead a series of recurring cycles. Proponents of this theory argue that it may explain certain observable phenomena in the structure of the universe, such as micro-oscillations in the cosmic background radiation. However, this theory faces challenges when compared with observations about dark energy and the universe's ongoing expansion. Another less common, but equally intriguing hypothesis is vacuum decay. This theory posits that our universe might exist in a false vacuum state. A quantum event could trigger a transition of the vacuum from a false stable state to a lower energy state, leading to a bubble of true vacuum expanding at the speed of light, erasing the current universe. While this may sound like the plot of a sci-fi novel, theories about quantum mechanics and the Higgs field indicate that vacuum decay is theoretically possible, though its likelihood is extremely low. Theories about other dimensions also offer interesting speculations about the fate of the universe. According to some hypotheses, our universe could be one of countless bubble universes existing within a larger multiverse system. When one bubble universe like ours becomes unstable or interacts with another, it could lead to its destruction or even a complete restructuring. This idea is inspired by theories about parallel universes and the multiverse in theoretical physics, where each universe may have different physical laws, resulting in countless possibilities for the birth and end of universes. Another scenario considered by physicists is death by heat death, a state where the universe gradually loses all available energy. In this model, the universe does not necessarily end with a sudden event, like the Big Crunch or vacuum decay, but instead slowly loses usable energy. Once all energy is evenly distributed and no temperature or pressure gradients exist to perform any work, the universe will reach a state of perfect but meaningless equilibrium, devoid of life, light, or any activity. Despite these theories about the universe's end, scientists are not only speculating about the fate of this vast space, but also striving to understand the fundamental forces that govern it. Dark energy, dark matter, quantum particles, and their complex interactions remain mysteries without definitive answers. Thus, studying the end of the universe is also a journey to comprehend the true nature of everything that exists around us. Whatever scenario may unfold, it reminds us that even the vast and seemingly eternal universe could have a definitive fate. These speculations and theories not only help us understand the universe better, but also encourage us to reflect on our place within a grander picture, where everything can begin and end in ways we can hardly imagine.